we're going to jump right into things. So I'm going to hand over the virtual mic to Rick to present his project. So take it away, Rick.
Awesome. Let's go. All right, I'll share my screen right away. Here. So one of the things that's fascinated me over time about computer science is how much of it you can do without computers. There's a history of building machines and doing a lot of CS theory and a lot of information theory even before the advent of computers. Turing invented the Turing machine in 1936. Anybody who hasn't seen what's up on the screen right now, the Kelvin's ball and disk integrator, it's an amazing piece of kit. It's an analog integrator. So another example of this that I've run into is one of the earliest examples of a machine learning algorithm implemented without a computer, like essentially before you would have had a computer to be able to do this. It was created by Donald Mitchie in '61, the Matchbox Educable Noughts and Crosses engine, or MENIS. So the way he did it, it's a very straightforward algorithm. He has all these matchboxes with all the possible states of the board for a tic-tac-toe game written on them. And then if you see there in the bottom right corner, he has colored beads representing each of those positions of a certain, you start out with an equal number for all of them. And then while you're playing, you look at the state of the board game, open the matchbox for that state, pick a bead at random, and that's the AI's play. That's the machine's play, and then keep them out. And at the end of the game, you've got a set of matchboxes for that round of play in front of you. And then depending on the outcome of the game, if the AI wins, you put back the beads that you took out for all of those boxes and then add a couple more for that color. If it loses, you leave them out. So you're reducing the likelihood you're going to draw that bead again. And if it's a draw, put them all back in and maybe add a small number in. So he implemented this in the 60s. It worked. He found the proof of concept worked out completely. And then, but then you quickly run into problems. One being it takes a long time to get through rounds. Another big problem is so many beads. For example, this is a representation from the implementation that I did, where this middle number here, at 265,000, this is after, I think it was about 100,000 rounds of play. You would wind up in that middle square when the board is blank with 265,000 beads. So you would need a matchbox if it's 5mm beads. That's over 1.5 meters long. Very big matchboxes, no room. So, but it was a proof of concept, and he stopped there. So what we've done since then, actually, let me stop this presentation for now. There's no extra resources. But that it really interested me that that algorithm and that simple sort of setup. So what I ended up doing was implementing that same setup just in Python. So with these, let me just move this screen out of the way. So let's look at an example of what one of these boards would look like. So here, this is a database that records the state of the board that the machine has seen each time, and it records the weights. So these all start out at 10, and then as it goes through each round of play, if the machine wins, it increases the likelihood that it'll hit that spot again from that configuration. If it loses, it reduces that number. So you see a lot in here that are less than 10. You see a 2 down here, a 4, ones that are much more. So it's won or drawn a lot on this. So if I can bring the chat up, I'm going to let you guys play against the machine. Let me get back over here. So we're going to go into here. I'm going to go into main. I'm going to play, that's fine for a number of rounds. Display this game. We're actually going to make that true. Come on now. Here we go. going to make that true. So we are going to display it on the screen. We're not going to generate random plays. I'm going to say false. So we're going to be playing as a human. And as we play, I'm going to turn these guys off. These are other machine opponents. And I'm actually going to play you, the human, against this one. A stupid baby. This is an untrained AI. No training rounds have gone into it at all. It doesn't even have a database yet. So the system, if it doesn't have one yet, it just creates one for us. So let's head over to the command line. And let's say, I'm going to start the game. So here's the game board. These are the positions 1, 2, 3, 4, 5, 6, 7, 8, 9. So yeah, nice baby icon. Exactly. So I actually have a macro that I can run in just a second. So hold off on the chat for now. I have a macro that I can run that'll let you guys play number by number in the chat. So just one person at a time, or everyone, who cares? Once I say go, put a number in the chat and you'll be able to play. So again, it's from the top left, it's just position 1, 2, 3, 4, 5, 6. So the baby AI has already gone once, and this is a terrible opening play. It's a dumb baby. It doesn't know what it's doing. It did this at random. So you probably will be able to win. So 1 second, let me start this.
Watching Zoom chat.
Did you guys hear that? Okay. Yeah, go ahead and type a number in the chat. Oh, it's
Playing 8.
There you go. Oh, well done. So it plays again right away. So somebody else has popped their round in there. Should go.
Playing 6.
Everybody's trying to play. Everybody's got an opinion on where we should play.
Playing 5.
Looks like it's going well. Hard to develop a strategy by committee.
Playing 3.
This is also another interesting part of the study. Oh, and you lost to a baby. Yeah, exactly. But
D. Not a valid play.
right. Let me turn off the macro. There we go. The macro just watches my third monitor and takes that spot from the Zoom chat and pops the number over into the command line. Actually quit it for now. So, but I don't know if you could see, like, it was playing kind of essentially randomly while I was playing. So let's go over here. I'm just going to let this stupid baby play against another stupid baby. Actually, just before we do that, let's go look at the baby opponent. Oh, stop that. Let's go look at our sweet baby boy. So that was after just one round. So we should see in the database. There we go. This is the entire game that just got played. So when it saw this blank configuration, it played that middle, or it played the left side square. So it's gone and increased the probability that it'll play there again if it sees a blank again. You can kind of follow the rest there. Most of them are 10s, some of them are increased because it won that round. We're actually going to go back here, make the baby play against another baby, cancel this human opponent. I'm just going to say, yeah, we're going to let it train for 1,000 rounds just to see what it looks like. We're actually not going to display the game this time. And we are going to generate random plays. So it's going to be true. So now it's going to be two AIs playing against each other using that same algorithm, using Mitchie's original menace algorithm. Is there anything else I need to change? Not really. So that should work out Go back to the command line. And I'm just going to let this run. So we'll come back to that in a minute. That'll just count down as it goes. So what we saw after running this a bunch, it was indeed learning, but it was able to learn a lot more completely than Mitchie's, because it could just run until it gets millions of records, or millions of data points in there. Can only hold, I think the maximum number of valid plays in tic-tac-toe is around 5,000, 5,400, something like that. So it would only ever have 5,400 records in the database. And if we use a proxy to look at sort of how well has it learned to play the game, you can see at the beginning, we've played 20 rounds in this graph. So it kind of is bouncing up and down, some wins, some losses. And then up to round 50, it's starting to really catch on and figure itself out. Here up to 500 rounds, it's mostly trending upwards. Still some losses, still some draws, but it's rising and rising. And then over time, this is kind of the curve that we expect to see. It just gets steeper because wins give it more of a slope. And then in the very end, what we sort of expect, because tic-tac-toe is a solved game, that results in draws once you've sort of worked out a strategy that works. And it came to this strategy by playing randomly and just learning from it. But we do indeed get a slope of about 1. So the way I have it set up is a draw is worth 1 point. So it's increasing by over time about 1 point. Getting closer and closer to that asymptote over time. Let's go back and see. Oh, good. 1,000 rounds are done. It's just we'll quickly go back and look at these. Who did we play against each other? The baby and the other baby. Let's go look at the other baby. So, yeah, just recorded this data over time from this other baby. Look at his board states. So he never plays first, so he still always has 10s in here, but he does play second and third and things like that. So that's the basics of implementing Mitchie's Menace. So next steps would be implementing different algorithms for tic-tac-toe and for other things. The trouble, if you can, those of you thinking ahead, the trouble with trying to implement something like this for chess, for example, is in chess there's something like on the order of 10 to the 40 or 50, I think, possible board configurations. So just this, we literally don't have the space to make a database based like this. This is what would happen if DeepMind from Hitchhiker's Guide was doing it. Just a giant brain that's all database records, and it would take years and years to search and index. Next steps that I was working on were more visualizations for the state space. Wasn't ready quite for this presentation, but I'll probably throw it up in the project updates. And that pretty much covers it.
That's awesome. Thank you so much, Rick. Great to see you.
I have a
thanks so
question,
much.
if that's all right.
Sure.
Yeah, we'll do, for sure. We'll do one question, then we'll also share the project link in the chat, and we can also add some questions there, but go ahead, Ryan.
One of the problems I had with game bots is that it gets too perfect and it's no longer fun. I like this approach is interesting because I can sort of, or at least I think you can sort of limit how good it gets, right?
Yeah.
Okay.
100% you can. And that's one of the things I played around with, actually. I have this settings file. It sets these initial weights. It also, you can change the win weight delta. So that's how much it increases by if it wins. This is how much it goes down by if it loses, or how much change for a draw. And then you can change the weight lower limit. So right now, like you saw those big databases before, it was like 250,000 versus 1, but there is no upper limit on that one right now. So you can actually put a capper on it so that it'll only get so high. And then put a lower limit on it as well. So it's still likely to mess up. It's still likely to make these non-optimal plays. Yeah.
That's awesome. Thank you.
Awesome. Well, thank you again so much, Rick, for all the work you put into the presentation, and audience participation is always fun. So great to see. And Rami has already put in Rick's project link in the chat, so feel free to ask more questions there.